Hello, good morning and afternoon. Thank y'all so much for joining us today for our next in our series for the Seminar Webinar series. Today we have Robert Skeirik, going to be talking about some AI type stuff and 4.0 reliability topics there. We're glad to have each and every one of you today. And again, this will be recorded and be able to be viewed later. And Robert, if you'd like to take it away.
All right. Well, thank you, David. Today I'm going to be speaking on the proper care and feeding of your vibration AI. There's certainly a lot of buzz in the marketplace about how to use an Internet of Things device and have the data come into vibration AI. And there are some serious considerations that should be looked at when you're evaluating implementing this technology. So that's the goal of today's presentation. So as far as proper care and feeding, that's also known as how to keep your implementation of AI from becoming artificial ignorance. And I'm afraid a significant number of the options in the marketplace represent the wrong kind of AI. So just quickly to myself, my name is Robert Skeirik. I am the lead instructor at Technical Associates of Charlotte. I've been doing vibration and predictive maintenance for 35 years now. I have a decade and a half of experience specifically with wireless vibration and the industrial Internet of Things. Currently, I have 13 patents in predictive maintenance, with a number of them addressing signal processing, specifically vibration signal processing. And as stated, I'm the lead instructor at Technical Associates of Charlotte, and I've actually presented in multiple languages on 6 continents. And to date, no one's invited me to Antarctica, but if they did, I would buy some cold weather clothing and I'd go. So if you're not familiar with Technical Associates of Charlotte, we have a pretty strong reputation in the marketplace. We are the original vibration training organization. We've been doing this now for over 40 years, and we've done face-to-face training with over 30,000 vibration analysts worldwide. We offer both public seminars, so you'll see there listed the ISO vibration analysis training, also time waveform, field balancing, and new this year also lubrication training. And we offer these publicly, but we also do on-site seminars where we will come to your plant site, customize the content to your program, your machinery, and even demonstrate the principles using your hardware or software. So Technical Associates of Charlotte training will help you both protect your assets and empower your analysts. So with that, let's get back to the topic of today, which is proper care and feeding of your vibration AI. And we'll start with the undeniable realities of AI. And the number one reality is that while computers are incredibly fast, they are also profoundly stupid. They will continue to do whatever task you ask them to do, whether it works or does not. Second is that artificial processes only work if they mimic what humans can do. And number 3 is the old adage, garbage in, you get garbage out. And number 4, you cannot predict what you cannot see. So, going back to our topic, what do you feed your vibration AI? And the key questions are, how do I avoid garbage in? And secondly, how do I ensure that I'm seeing the data that I need to be able to analyze and predict the condition of the machine and when it may fail? So the answer to that is measuring vibration in 3D. And no, I do not mean horizontal, vertical, and axial. It's a different 3 dimensions. The first one is the frequency range. How high frequency is high enough? And if I'm not measuring into the high range, what am I missing? The second dimension is amplitude. And the question is, how much is enough? And what else will tell me when to intervene if I'm not tracking the amplitude of the vibration defect signals? And the third one, which is largely overlooked, is the sampling rate. And I'll go into this, but the sampling rate, the question is how fast is fast enough? And if I'm not sampling fast enough, what events am I missing? So if we had a device with a limited frequency and amplitude range, and then also with a lower sampling rate, which would fit with the lower frequency range, I would consider that inadequate for machine monitoring. We could expand the frequency and amplitude a little, but without expanding the sampling rate significantly, that's still a poor solution. And we can again push out frequency and amplitude, but if we're not pushing out the sampling rate, it's better, but it still can miss key defect signals. And then finally, if we push out into a high frequency range, high amplitude range with a very fast sampling rate, that is the best solution. So we're going to look at each of these axes individually. So the first one is frequency. So what's shown in the graph here is the ISO, the International Standards Organization vibration measurement range from their standard 10816, which goes either from 10 to 1,000 hertz, or it's been updated to go from 2 to 1,000 hertz. And each of these little dots represents devices that are available in the market. And what they will tell you reliably is they will tell you about unbalance, misalignment. They'll pick up belt issues, bent shafts, shaft rubs, also mechanical looseness, soft foot, and resonances. So basically it's telling you about the shaft, the coupling, the structure, and the foundation. However, it's missing the 2 key production killers, which I would say, based on 3.5 decades of experience in this market space, rolling element bearing defects and gear defects are the 2 main things that shut down your facility. So the ISO range, we're going to park it down here in this little red box, and now we're going to extend out to 5 kilohertz, 5,000 hertz, and now we can start to reliably pick up the bearing defects and the gear defects. However, even this 5 kilohertz range is missing the 2 primary root causes of our main killers, and that's cavitation on pumps and inadequate lubrication. So we're going to take this expanded range and we're going to park it again down in that little red box. And now instead of capping it at 5 kilohertz, we're going to go out to 20 kilohertz. And also extend the input range from 10 or 20 Gs up to 50 Gs. This is where we're going to get the best indication for sure of inadequate lubrication and pump cavitation. And there are a few choices out here that actually extend into this range. I would recommend that you focus on those solutions. If you're not measuring out to the full frequency range, you're missing the what in the equation. The nature of the defect on the machine shows up with this expanded frequency range. If you don't have the expanded input range, what you're missing is the when. You're missing the indication of severity that tells you when you need to intervene. And unfortunately, 95% of the solutions offered in the market today live inside that red box. And yet, based on over 10 years of study by the largest independent vibration service company, 1 out of every 3 industrial failures has key defect signals that show up in that yellow rectangle. So if you don't have full coverage of this entire field, then you either will miss an impending failure, or you may know it exists but misinterpret when it will occur. So let's focus on the frequency and what is the recommended frequency range. And I'm showing a couple of different sensor types here on the left. Piezo sensors are what have been used for 70 years now. MEMS are the newer microelectromechanical systems. They're chip-based accelerometers. Regardless of what sensor type is in your device, it needs to measure at least recommended 2 hertz to 10 kilohertz. What's better would be 1 hertz to 15 kilohertz, and what would be best is to measure from 1 hertz to 20 kilohertz. So that would be my recommended range to look for. If you don't measure out into these higher frequencies, then the system may not be able to see events such as bearing and gear defects, also the root causes such as lubrication and cavitation. There are some electrical defects, rotor bar damage that show up in these high frequency ranges as well. So the result is that defects that might otherwise have been caught could remain undetected and lead to a surprise outage, resulting in you still getting the call in the middle of the night. So with that, let's move on to the second axis, which is amplitude. So how high do you need to measure? Well, I'm going to put up some very, very high extreme vibration levels. So 3 inches per second, that's 10 times the ISO limit. There's a number of different examples there at different frequency ranges, all extremely severe levels of vibration. And yet all of these, when expressed in acceleration, are well below 5 Gs. So that would suggest, if you can measure to 5 Gs, that you have all the amplitude range that you need. And that is unfortunately the conclusion of some of the solution providers that don't really understand machinery analysis. So let's look at a case history. This is a garden variety belt-driven fan from an 1800 RPM motor. And what I'm going to show you on the left side of the screen over a 60-day period is the trend of the ISO vibration level. And what you see there over that 60-day period is that it never reached even the alarm level 1, let alone the ISO level, which is represented there by the red dashed line. And all of these values, all of them are well below half of a G. So 5G sounds wonderful, but the problem is that if you do special signal processing, you find that at the beginning of this 60-day period, it was already impacting on the bearing about 5 Gs. And as it moved through the failure stages of bearing defect, it increased up to and above 40 Gs. And that was simply done with the same accelerometer, but by doing more intelligent signal processing. So the data is there up to 40 Gs and beyond if you know how to look for it. So the recommended input range, regardless of the sensor type, a minimum of 25 Gs. What would be better is to go up to 40 Gs, and what would be best is to be able to measure up to 80 Gs so that you can track the severity of these defects. And you see the asterisk, that has to be combined with some good electronics that have a low noise floor. Otherwise, you'll see the high amplitudes but miss the low signals. So if you don't have sufficient input range, if the system can't tell you these high amplitudes, you may not be able to track the progression of a defect towards failure. So that means you may actually even know the fault exists, but not be able to determine when the shutdown is required, so you still get the call in the middle of the night. And with that, we'll move on to the least understood aspect, which is the sampling rate. So sampling rate, why is that so important? Well, I just did some research on this at the end of last year, and pretty striking results. So what we did is we simulated a high frequency defect, so an 80 kilohertz event at 1G amplitude, and this was a triple pulse to simulate a bearing defect, inadequate lubrication. But the entire event occurs over 30 microseconds. So this is our sample that we fed from a signal generator, so we know the amplitude is exactly plus and minus 1G. So it creates this envelope around the signal whereby, except for the impacts, what's in that red box is noise. That's the noise floor. Now we're going to look at this signal and process it with 200 kilohertz sampling rate. So that's 200,000 times per second. That allows us to have an Fmax of 80 kilohertz. We see the entire time duration of the signal, but the amplitude is already dropped, and you'll see over here, if you can see my cursor, that the shape of those three pulses is now significantly different. That's at 200,000 times per second. Well, let's cut that in half to 100,000 times per second. And now look at the picture. The picture tells the biggest story. I still see there are three pulses, but I have lost, over here in the table, more than 3/4 of the amplitude of the original signal. So let's cut it in half again and watch what happens over here in the graph. That is now just dropping my sampling rate by a factor of 4. I have pretty much lost the event, and I've lost over 90% of the actual amplitude of what's occurring. As we continue to cut the sampling rate nominally by a factor of 2, you'll see that it is now in the noise floor. As I go down to 12 kilohertz, 5 kilohertz, and 2.5 kilohertz, it's now gone. And the problem with this fact is that 90% or more of all the devices available in the market actually measure in this red box, meaning that they would not be able to see this event at all. So what is the recommended sampling rate? Again, regardless of the sensor type you use, good, you have to be sampling at least as fast as your fastest failure mode. Better would be at least 2 times as fast as your fastest failure mode. And the best is at least 5 times your fastest failure mode. So how fast? Well, if we're talking rolling element bearing and we're talking about lubrication, these events can happen in fact, 30 to 40 kilohertz is the general range for detecting lubrication. And so 5 times that puts you around 150 to 200 kilohertz. So if you want to know about lubrication effectiveness, you need very fast sampling rates. And again, you'll notice the asterisk says this has to be combined with the high frequency range and the high input range in order they work together to give you the real indication of machine condition. So what happens if you don't have sufficient sampling? Well, you will at a minimum, underestimate the severity of the event or defect by a huge factor. Or worse, the machine may run to failure with no warning at all. So you may even be aware there's a developing fault, but you'll still get the call in the middle of the night. So in summary, we have 3 dimensions. And again, this is not horizontal, vertical, axial. It is the frequency range, the amplitude range, and the sampling rate. So these are the parameters that, in my opinion, need to be evaluated if you're going to consider an IIoT solution. And if you don't address all 3, then you will have some easy wins. So even the simplest, most basic solution out there, it will absolutely identify unbalance. It will find your misalignment. It will find the looseness. Those are easy wins. It may even catch some of the bearing defects, but I promise you it will miss others. And you will still get that call in the middle of the night. So the question to ask your management is, what percentage of the developing rolling element bearing defects are they okay with you missing? And if that answer is 0, then you need to be seriously looking at all 3 of these dimensions in the vibration monitoring technology. So, and it doesn't really matter if it's a human or a computer. So you could have the best AI in the world and still experience the bad day when your production asset fails without warning, and you still get that call in the middle of the night. So that's this presentation on how to feed your vibration AI. It's also how to evaluate the monitoring capability of any IIoT Industry 4.0 digitalization solution. So thank you, and I'll handle questions. David, if you have any you want to pass on from the attendees.
Yeah, sure. Thank you, Robert, for that presentation there. So we had a few people put some questions in the chat. You feel free, anybody feel free to put them in there, or maybe try and raise your hand too, I think. So the first question we got, what's the sampling rate for iCare wireless sensors?
The iCare wireless sensor historically has sampled at 80 kilohertz. As I mentioned, I have 13 patents. I have my 14th currently in process right now, and they're largely focused on signal processing. So based on that, in the latest iCare device, because I've input into their development specs, they've actually doubled that to 160,000 kilohertz. And to my knowledge, that is the fastest sampling rate in the industry of any device by at least a factor of 2. And yeah, so answer is 160 kilohertz, 160,000 times per second.
Thank you. Anybody that has questions should probably also be able to unmute yourself if you have a question too. So one other question we had in the chat, how long does the high response affect sensory battery life? So I guess the sampling rate. Mm-hmm.
So running the processor to be able to detect 160,000 times per second actually does require a slight amount of additional battery. But for all of your balance of plant equipment, which is the primarily application for IoT, so all your motors, pumps, and fans, the amount of time you need to collect data is very short. So there is no significant difference. In fact, it may actually cost less battery life to do the high frequency measurement than to do the standard vibration measurement. So and this has been a learning curve. I can promise you, with different vendors, and I have input into the development specs of several vibration vendors. initially it was eating batteries, but it's been a learning curve to learn how to do it without negatively impacting battery life.
Very good. That's all the questions I saw in the chat. Did anybody have a question you'd like to ask? Feel free to unmute yourself or raise your hand or anything. Anybody?
Yes, this is Roberto. I have a question regarding, I guess it's related with battery life. Um, so what are the, I guess, what are the parameters that you will need to take into consideration to decide if you want to go with the highest resolution, let's say highest frequency, highest sampling rate, highest. So, because obviously we cannot just increase in all the sensors the highest, frequency, amplitude, et cetera, all the parameters that you mentioned. So we cannot do that because obviously maybe you will affect the battery based on what you just responded right now. So, okay.
No, it's been a learning curve. I
Okay.
can tell you when I started advising iCare on their product development, even their own service people avoided this technology because it chewed through batteries.
Mm-hmm.
But with over the last 3-4 years, the technology has advanced, and even pushing it up to the 160,000 samples per second, it's now possible to do that very, very efficiently in terms of battery life. And I want to be clear too, the high frequency measurement is not a replacement for traditional vibration. Basically, if you think of the vibration spectrum, traditional vibration, and I don't know which way is left and right for the audience, so if I get this backwards, just forgive me, but traditional vibration has a high pass filter and it's only looking at the lower frequency. The special measurement that I showed is actually killing all the low frequency and only looking at the high frequency out to 160 kilohertz. And those two fit together. And the lower frequency parameter, as I mentioned, tells you about the shaft, the coupling, the casing or structure of the machine, and the foundation. And the high frequency data primarily tells you about bearing and gear, plus your two root causes, pump cavitation and inadequate lubrication. So you need both. If you don't have both, I would argue you do not have an automation solution that I would trust.
Okay,
Very
and
good.
how do we know what type of setups do we have in our system? Do we need to talk to the analyzer to ask, what are we at the max frequency for the sensors?
So it depends on the vendor.
I mean,
Some vendors actually allow you to set the Fmax, which changes the sampling rate. And I don't know which is left and right for you, but that's true with all the solutions out there in the low frequency where you set the Fmax, it determines the sampling rate, and it's roughly a factor of 2. But in the high frequency, you always want to do the highest sampling. So you're always going to do this as fast as the device can do. So you don't configure this. You just ask for the data.
Got it. Thank you.
Very good.
Yeah.
Thank you. Anybody else have any questions? Okay. I don't believe anybody else raised their hand or put any more in the chat. So thank you, Robert, again for presenting this information and for sharing this with all of us. And we thank you that each and every one of y'all joined today. Again, this has been recorded, so we'll get it sent out to y'all, and we'll hopefully it'll come, I think, today or sometime very soon. So thank you so much, and
All right, I'll also put my email in the chat. So if any of you have questions and you'd like to reach out directly, you're able to do that.
Yeah, there you go. Perfect. So thank y'all for joining, and we look forward to seeing you on our next one, which will be in August. And that'll be my dad, Jim Berry, presenting some information on the time waveform analysis. So thank you again for joining us today on our second of our 3 seminar webinar series, and we appreciate it. Y'all have a good weekend. Bye-bye.
All right. Thank you.
Thank you.